this computer. Okay. So we're going to have the same situation as last time where the first minute or so will be missing. Maybe I should just quickly scroll back to the previous whiteboard so just we can look at it for a second. And if you want to go to the video, you get an opportunity to see this whiteboard. Okay, you can stop here and then scroll forward again. I think as we continue to do this, hopefully we'll get the kinks worked out. Okay. So what was I saying? So the total energy is just some integral over all possible energies between 0 and E Fermi. So it somehow makes sense that the average energy would be something in between. And the average energy is not a half E Fermi, it's 3/5. And that's simply because there are more states with higher energy than there are states with lower energy. So the mean energy is not a half E Fermi, but a little bit more than that. So the mean energy is, somewhere here. It's the magic 3/5. Okay, so so this expression, you can also rewrite this, say, in terms of the energy density of the system. So the energy divided by volume, which I will also sometimes just write as a sort of script E, is, you divide the right-hand side by the volume. So it's 3/5 times the density times the Fermi energy. Okay. So this expression explicitly shows something I already said last time, which is that obviously, so this is at 0 temperature, that in a Fermi system, even if the temperature is exactly 0, the energy is not 0. And that's simply because we cannot put all the particles into the 0 energy state. Once you put 2 particles in there, one would spin up and one would spin down. All the other particles have to go to higher energies. And, as a result, the energy cannot be 0. In fact, you see from this formula that the energy density of the system will scale as the density times the Fermi energy, but we saw that the Fermi energy also scales as density to the 2/3. So overall, this will actually scale as density to the 5/3. So if you compress a very cold system of fermions, and the energy density will have to go up, and actually goes up quite quickly. It goes up faster than the density of the gas. So this is different from a classical gas. For a classical gas, if you increase the density, pressure only goes up as N, okay? So this brings me to the fact, so we can also try, now that we know what the energy density is, we can also try to figure out what the pressure is. And the easiest relation to use for that purpose is something that you should be able to find in your notes somewhere, which is that we observed at some point that the energy density plus the pressure is equal to mu times N plus S times T. So I think I assigned that as a homework problem at some point. So it follows from the homogeneity of the system, the fact that, say, the total entropy is the volume of the system times the entropy density. And then entropy density is only a function of density and, say, energy density or some such thing. So we showed that a little while ago that that was true. So if you use that relation at 0 temperature, then obviously the entropy term goes away and you can solve it for pressure. So then the pressure of the system is mu times N minus E, or minus the energy density. We saw that mu in the ultra-cold Fermi system is just the Fermi energy. So the first term is epsilon Fermi times N. And we just computed the energy density and found it to be 3/5. So that was 3/5 times the Fermi energy times the density. So then 1 minus 3/5 is 2/5. Okay. So, and you observe that again, the pressure will increase as N to the 5/3 as you make the system more and more dense, because the Fermi energy will increase as density to the 2/3. So that's this magic fact that I alluded to last time, that if you take a system of fermions, there's always a source of pressure, even if there's no interactions at all. So if you take a bunch of fermions and you try to compress, then the pressure will rise, even if there aren't any repulsive forces or repulsive potentials or anything. And that actually is kind of important in nature as a sort of ultimate reservoir of pressure that can resist collapse. That, if you have a bunch of particles that have some kind of long-range interaction that's actually attractive, then they will typically condense and form, a solid or a blob of liquid. And the question is, what prevents them from collapsing further and further if there's some attractive interaction? And the answer for many systems is that ultimately it's Fermi pressure. It's sometimes called Fermi degeneracy pressure. Okay. And I wanted to, so I have an example of this, or actually a whole couple of examples of this on the homework, but I just wanted to illustrate this with sort of one example where we can kind of see what the numbers are. So the example I wanted to discuss was a neutron star. Because a neutron star actually is one of these objects where it's Fermi degeneracy pressure that's the ultimate source of pressure in the system. There are actually, by the way, two kinds of star where that's the case. So there's a type of star called a white dwarf, which is what will happen to the sun eventually when the sun runs out of fuel. So the sun obviously is currently stabilized by the fact that there's nuclear reactions in the core. The system is very hot. It's a hot plasma. And the pressure in the system actually is basically thermal pressure in a more or less ideal gas. So roughly speaking, the pressure is something like n times the temperature at the center of the sun. And that's the thing that currently determines the radius of the sun. But eventually these nuclear reactions will cease, and so then the sun will start to contract. And the question is, what prevents it from collapsing into a black hole? And for the sun, the answer will eventually be that there are a whole bunch of electrons. It's currently a plasma. So there are a whole bunch of free electrons. If you keep compressing them, then eventually you get to Fermi degeneracy pressure of these electrons, and that will stabilize the star. And a star like that is called a white dwarf. So a white dwarf is an object that's stabilized by electron degeneracy pressure. Now, there are some systems, stars larger than the sun, for which electron degeneracy pressure is actually not quite enough to overcome gravity, because gravity is a long-range force. If there's more and more stuff, then you actually get more and more attraction. And so there's a sort of next thing that can potentially save you, and that's the Fermi degeneracy pressure of protons and neutrons. And a system where the main source of pressure is this Fermi degeneracy pressure of neutrons, protons, called neutron star. Okay, so I have to tell you something about the star. In principle, by the way, you can work that out from the following fact. So what a neutron star is, roughly speaking, is an object with a radius on the order of 10 kilometers or so, and a mass that's roughly the mass of the sun. Okay, typically a little bit bigger than that. So, so you have a whole solar mass, but compressed into a spherical volume of radius roughly 10 kilometers. So you can work out what the density is just by looking up, what the mass of a single proton or neutron is. But so here I will just tell you what the density is in terms of the number density of neutrons. And very roughly, it of course varies in the star. It's a little more dense in the center and a little less dense outside. The density ends up being more or less the same as the density in a single large nucleus. So if you take a lead nucleus, for example, that's 200 neutrons and protons in the radius of a few Fermi, the density inside that spherical, that sphere of radius 5 Fermi is more or less constant. It's sometimes called nuclear saturation density. And that density is about 0.15 neutrons or protons per Fermi cubed, where a Fermi is just a name for 10 to the minus 15 meters, okay? So Fermi is just a convenient unit in particle and nuclear physics, because again, one nucleon is roughly a Fermi across. in atomic physics, everybody's favorite unit is an angstrom because an atom is roughly an angstrom across. So an angstrom is 10 to the minus 10 meters, and a Fermi is 10 to the minus 15 meters. Okay, so if I give you the density, then from the magic formula that we have, you can now work out what the Fermi wave vector is. So the Fermi wave vector was the third root of the density. So there was a factor of 3 pi squared density to the 1/3. Okay, so since the density came in units of Fermi to the minus 3, this Fermi wave vector will now have units per Fermi. So this is 0.3 pi squared times 0.15 to the 1/3 times an inverse Fermi. Okay. So this is roughly of order 1. So 3 pi squared, well, pi squared is roughly 10. So this is 1.5 times 3, that's about 4.5. And I don't know, what's the third root of 4.5? That's 1 and a little bit. So we don't want to be super precise here. It's something like 1.5 Fermi to the minus 1. Okay. So now I can try to work out what the Fermi energy is given that Fermi wave vector. So epsilon Fermi is h bar squared k Fermi squared over 2m. So this m is now the mass of a neutron or a proton. Actually, in a neutron star, it's mostly neutrons. Doesn't actually matter all that much anyway, because the masses of neutrons and protons are very close together. So, so at this point, you can, of course, just look up what h bar is. It's a very, very small number. But there is a kind of neat trick that people like myself actually use a whole lot, which is that h bar is a number that's very difficult to remember because it's so goddamn small. But the mass of the proton is also a mass that's very difficult to remember because in units of kilogram, it's so small. So the trick is to multiply both of them through by c squared. So you can write this as h bar c squared k Fermi squared over 2m c squared. Okay, and why is that useful? Because mc squared is now a number, mc squared is now an energy. And that energy in suitable units is actually not super hard to remember. So a set of unit that, again, is kind of popular in nuclear particle physics. So energies in principle, of course, are quoted in joule. That's the appropriate SI unit. But people who work with accelerators in either atomic or particle or nuclear physics often will quote energies in electron volts because, if you have a charged particle and you accelerate it by letting it transverse a certain amount of potential, then that's an energy. So you can just quote, if you took an electron and you accelerated it by applying 1 volt, then it has an energy that is 1 electron volt. And in principle, you can compute that in joule by just putting in what E is in coulombs, but it's often easier to remember just what the number is in electron volts. So the mass of a proton in electron volts is 1,000 mega electron volt or 1 giga electron volt, roughly speaking. So this is 1 over 2,000. Again, that's not precisely right, but close enough. Mega electron volt, that's twice the mass of a neutron. And then the next trick is that h bar c, again, h bar is sort of a product of a very small number and a very large number. But you can think of h bar c as a kind of conversion factor between energy and distance. So you can actually quote h bar c in units like angstrom times joule, or you can quote angstrom times electron volt, or mega electron volt times Fermi, or some such thing. And what is amusing is that in MeV Fermi, it's a very ordinary number. So h bar c is very close to 200 MeV Fermi. And you see that actually tabulated in a lot of books on atomic or particle physics, what h bar c is in, say, atomic units, which is kind of angstrom electron volt, or particle units, which is mega electron volt times Fermi. So it's 200 MeV Fermi squared. And then we saw that, so K Fermi was 1.5. So that's times 1.5 inverse Fermi, and that whole thing squared. So now you see that this is actually all very ordinary numbers. So obviously the Fermis cancel. There's 2 powers of MeV here and 1 power of MeV in the denominator. So this is overall an energy. So we should still have units of MeV. So that works out. So 200 over 2000 is about 1/10. And then we have 200 MeV times 1.5 squared. So I don't know, what is 1.5 squared? That's somehow 2 and a little bit or something like this. So let's just write 200 MeV. So 200 divided by 10, that would be 20 MeV. And 1.5 squared is what, 2.3 or something like this, 2.25. Okay. So then 200 divided by 10 is 20. And so this would be about 40 MeV or so. Again, you can easily do that more precisely. So the Fermi energy in a neutron star is about 40 MeV. There's various things you can try to compare that with. So you saw that the rest mass energy of a nucleon is about 1,000 MeV. So 40 MeV is about 5% of that. So you see that the neutrons in a neutron star are sort of moderately relativistic. They have an energy that's a sizable fraction, but not yet, 50%. So 50% would be very relativistic, or 90% would be super relativistic. So the neutrons in a neutron star, they're kind of moderately relativistic particles. And you can then go ahead and compute, for example, what the energy density is and what the pressure is and so on. And again, I have a bunch of examples of that on the homework. And so you can, for example, go ahead and try to compute what the pressure is in, say, ordinary units, how many atmospheres. You could ask yourself, for example. So there are all sorts of little calculations that you can do. And again, at some point, we actually still plan to do a sort of regular final. And I'm sure that's the sort of problem that, again, at least one of these will be somewhere on there, that we try to generate numbers for what is the energy density or the pressure of some kind of Fermi gas. So that's always a popular subject. Okay. So if there aren't any questions about this, I would go on to something completely new and different. Okay. So the subject could not be more different. And I was going to start on the subject of doing kind of numerical simulations of statistical mechanics systems, because that's something that's really quite important in many, many different areas of physics. So I think the textbook just calls this subject computation. Okay, so what is the issue? The issue is simply that in principle, we have a perfectly good definition of this partition function. So the partition function is, some overall states of the system. Okay, like so. But as a practical matter, that's usually almost impossible to compute unless you have a bunch of particles that are just non-interacting. So if you have a bunch of particles that are not interacting, then you just compute the partition function for a single particle. And since, if the energy is just the sum of many single particle energies, the partition function will be a product of many different partition functions. And the free energy, which is the logarithm, will just be the sum of these different free energies of individual particles. But for a real system where the particles actually do interact, there really is no good way to compute this sum. I mean, you would somehow have to diagonalize some enormously large Hamiltonian for many, many particles and then compute all these energy eigenstates and then somehow sum them up. And even for very simple systems, there's really no practical way of doing that, okay? So solving the Schrödinger equation for anything that has more than n particles is sort of practically impossible. And so you might think that the whole thing is kind of hopeless, but the partition function is actually in some ways a sort of super convergent thing, because we're summing all these exponentially small terms. So if you could somehow manage to figure out which ones are the important terms. So in principle, there's gazillions of states, and you're supposed to sum over all of them. But for many realistic systems, there is a sort of typical state, and if you could only figure out what it is, then you could actually compute the sum very efficiently. And it's effectively what you try to achieve in numerical simulations. And instead of somehow explaining that in full generality, for just a simple toy model, and then we will find an algorithm that's actually really quite general. And the toy model, which we will look at, is called the Ising model. So Mr. Ising, I think that was actually Ising's thesis. So he was given that model. Solving this model was supposed to be his thesis project. Okay, so the Ising model is a model for a magnet. And we imagine that this magnet lives on a lattice. And just to make it easier to draw, I will assume that it's just a two-dimensional magnet, so living on a two-dimensional lattice. But the Ising model is easy to generalize to 3 dimensions or 1 dimension. Okay, anything you want. So there's a two-dimensional lattice. And what makes this a model for a magnet is the fact that we imagine that on each of these vertices, we have spins. And we will take the simplest kind of spin. We assume that the only quantum thing about the spin is that it's discrete, so that it can either point up or down. So on every one of these vertices, we have a spin-a-half particle. Okay, so then the spin of that particle, so I just labels this vertex, is h bar over 2 times some little s, and that little s is now just plus or minus 1. Okay, and that will be the only thing quantum about the model. It's a model of classical spins, but it's made quantum by the fact that the spins are discrete. They can either point up or they can point down. And of course, what potentially makes it a model for a magnet is that, all of these little spins, they can become aligned, and then that would be like a ferromagnet, or they can be disordered, and that would be like a paramagnet. Okay. So in order to get a partition function for this, we need some kind of Hamiltonian, which is now a completely classical Hamiltonian. So the Hamiltonian for this system is a sum over nearest neighbors. And I will for now write this as bracket ij, and I'll explain that notation in just a second, times some kind of coupling strength times the product of Si and Sj. And remember that Si and Sj are just numbers that are either +1 or -1, okay? And they can potentially be, this is being a model for a magnet, it can potentially sit in an external field. And the external field will simply couple to the magnetic moment of the spins. So the coupling to the external field, I will write as -h, which is the external field, times the sum over all spins, times Si. So this is my Hamiltonian. Okay. And again, so what I mean by bracket ij is simply, you should imagine that there is a spin labeled by I, and that spin has 4 neighbors, okay? So this is my spin I, and then it has a bunch of neighbors, which I label by j. And this bracket ij is just a sum over these four connections. So bracket ij is just a sum over nearest neighbors. So physically, what does that mean? It means that, so these spins interact. And in fact, in order to have a model for a ferromagnet, we need something like that, because in order for the spins to align, there must be some kind of interaction so that they preferentially want to show in the same direction. So every spin must somehow know what other spins are doing. Now, in principle, that could be a complicated interaction that has somehow a long range, so that every spin kind of knows what all other spins are doing. So that's possible, but this actually turns out to be a pretty good caricature of what happens in real systems, that roughly speaking, every spin just sees its nearest neighbors, and it knows whether the nearest neighbor has the same alignment or a different alignment. And you can see that the way this Hamiltonian is formulated, if you take this coupling J to be a number that's greater than 0, okay, so then Si times Sj, if two neighboring spins are pointing in the same direction and they're either both +1 or both -1, so if they're pointing in the same direction, the product will always be a positive number. And so if J is a positive number as well, then you get a lower energy in this Hamiltonian because of the minus sign in front. You get a lower energy by aligning them, provided that J is positive. So this interaction is then sometimes called a ferromagnetic interaction. Okay. And if you change the sign, now the interaction favors to anti-align neighboring spins, so that the state of lowest energy is a sort of checkerboard where alternating spins, you have one spin up, spin down, spin up, spin down, and so on. And a state like this is sometimes called an anti-ferromagnet. Okay. So we will mostly, when we play around with this numerically, we'll mostly consider the ferromagnetic case, but both of them are kind of interesting cases. Okay. So, so we had this H. Again, you should think of H as being in an external magnetic field. And you saw that this H, it couples to the sum of all spins. So you can think of the sum of all spins as something like the total magnetization of the system. So you can define M as a sum over all I of little si as the total magnetization. You should note that the system is, in some ways, this Hamiltonian is not really written in physical units. Like for this to be truly, since the SIs are just ±1, so for this to be truly a magnetization, I would have to multiply it by a magnetic moment. So if this was a system of electrons, then really I should multiply this by the Bohr magneton for a single electron or something like this. Okay. But since for now it's just kind of a toy model, we're sort of not really putting physical units on it. So this would be the total magnetization, and you can define something like a magnetization density, which would be the total magnetization divided by the number of spins. So N is the number of spins. So, so this model now really does define a partition function, because so the sum over all states, so if you try to define a partition function, so what are all the possible states of the system? So it's a lattice of n spins, okay? And each spin has only two possibilities. The spin can point up or the spin can point down. So for every single spin, we have two possibilities and we have n spins total. So this sum is effectively just a sum over 2 to the n states. Okay. And just being completely classical, it's trivial to compute these energies because for every single one of these states, you just have to figure out what the nearest neighbors are doing, and you get a +1 if the nearest neighbors are aligned, and you get a -1 if nearest neighbors are anti-aligned. And you can also then include this external field, and what matters for the external field is simply what the total sum of these pluses and minuses is. Okay, but you kind of see what the problem is, which is that even for a super simple system like this, the total number of states grows exponentially. So if you make the, if you did this for 10 to the 23, then the total number of states of your system is 2 to the 10 to the 23. So it's some absolutely humongous, enormous number of states that you would have to sum over. So the Ising model is so simple that for relatively small lattices, you could still do that. But it very quickly becomes totally impractical to compute this partition function, okay? And it does not in any obvious way factorize. Although for the two-dimensional Ising model, by the way, it is true, and you can easily find that in books, there is a trick for factorizing the partition function of the two-dimensional Ising model, which if you want to look at it, by the way, so this model was solved by Onsage. And if you ever have too much time on your hand, you can easily look this up on the internet and see how to compute this partition function. So for 2 dimensions, it turns out that there's a trick. And for 1 dimensions, it's almost trivial to do it. So again, actually, if you have too much time on your hand, you should try to do it for a 1-dimensional Ising chain. That's not super hard. There's a sort of easy trick because every particle really only has 2 neighbors. So for 1 dimension, it's almost trivial. For 2 dimensions, there's a sneaky trick invented by Onsage. And for 3 dimensions, people have been thinking about it for almost 100 years now, and nobody's been able to do it. It's really just a math problem of enumerating all these states. But yeah, it turns out to be very hard. Okay. So, but what do we expect? I mean, if we could somehow solve it, compute the partition function, you see that, what you would want to compute is something like, what is the average magnetization of the system? And the average magnetization of the system for a partition function like this would just be the derivative of the log of z. So if you could somehow compute z, again, you could compute the free energy, which is the logarithm of z. And then if you computed something like the derivative of the free energy with respect to this external potential, then you can bring down a factor of the magnetization. So that would be proportional to the mean magnetization of the system. So if you could somehow compute that, you could compute the magnetization. So what do we expect to see? Well, if this really is a good model for a magnet, then it should behave just like a kitchen magnet. And the way a kitchen magnet behaves is that if you compute the magnetization as a function of the temperature, then at very low temperature, the state of lowest energy, if you have J greater than 0, is for all the spins to align. So for low temperature, you find that there's a non-zero magnetization, but that magnetization drops as the temperature increases, and it drops all the way to exactly 0 at some particular temperature. And so that temperature is known as the critical temperature, or sometimes also called the Curie temperature. Okay. So this point is called Tc, which is, the C is either for critical temperature, and in the case of a ferromagnet, the critical temperature is also sometimes called the Curie temperature. So this, by the way, so first of all, why does this happen? Well, loosely speaking, it happens again at low temperature what dominates is that you just want to find, in the partition sum, the states with the lowest energy somehow dominate, and the state with the lowest energy is one where all the spins are aligned. Okay. But as you increase the temperature, the suppression of higher energy states becomes less and less. So it's easier for the system to go into high energy states. And of course, there are many more high energy states than there are low energy states. Because if you have a state of the system where all the spins are aligned, that's a unique state. Out of all these 2 to the n states, there's just one that looks like that. But there are many, many, many more states in which the spins are disordered. And so if you wish, at high temperature, eventually just entropy wins. There's so many more states in which the orientation of the spins is essentially arbitrary that eventually the magnetization drops to 0. What is a little bit of a miracle, if you just look at this Hamiltonian, is that that should happen as a sharp transition. So that's why this is called the critical temperature, that there's really one point where it's not the case that the magnetization now becomes very small. It really becomes exactly 0 at that point. Okay, so that's why it's called a critical point. And another sort of language that's used in this connection is that we say that the magnetization is an order parameter. So this M, or the big M, is an order parameter. And what one means by an order parameter is that the system has 2 phases. So there are 2 phases. And there's a sharp distinction between them, because there is a quantity called the order parameter, which is exactly 0, not approximately 0, small or something like that, but exactly 0 in one of them. So there's a magnetized phase, where M is strictly greater than 0, and there's a disordered or non-magnetized phase. Disordered, where M is precisely 0. Okay. So a situation like this is called a phase transition. And this particular kind of transition where it happens continuously. So in one phase, M is greater than 0, and the other one, M is equal to 0, but it goes to 0 continuously. It's just that there's a discontinuity in the slope. That's sometimes called the second order phase transition. There are other kinds of transitions, which we'll actually see in just a second, where the order parameter discontinuously jumps from one value to another. That's sometimes called a first order transition. So indeed, there's something that you can look at here, which is called a phase diagram. Because we can study that not solely as a function of the temperature, we can also study it as a function of the applied magnetic field. Okay, so I can draw a 2-dimensional diagram, like so, where on one axis I plot H, and on this axis I plot T. Okay, so at H equal to 0, that's roughly what we just talked about. So if the temperature is sufficiently low, the system is magnetized, and then there's some magic point where it stops being magnetized, and we call that TC. Okay. But now, one of the things you can explore is that if you're below TC, you can ask yourself what that looks like as a function of H. And so what that looks like is as follows. So now I can pick a different plot. It's a little pretty here. So I try to plot the following thing. I plot the magnetization. As I go across this line, I plot the magnetization as a function of H. So I'm in a system that's magnetized, but they actually are. I lied a little bit earlier when I said there's only one spin where only one state where the spins are all aligned. Exactly 2 states where the spins are all aligned, because they can either point exactly up or they can point exactly down. And in a ferromagnet, the system somehow has to spontaneously decide what it wishes to do, whether it wants to go all up or wants to go all down. And in the presence of an external magnetic field, there of course is a preferred direction. So the external magnetic field will provide a slight edge for the states in which the spins are aligned with the external magnetic field. So what we expect to happen at zero temperature is that if the magnetic field is negative, then the magnetization is also negative. And if the magnetization, if the external field is positive, then the magnetization will also be positive. So you get a discontinuous curve like this. So this would be at zero temperature. If I make the temperature a little bit higher, what's going to happen is that the magnetization, now there's a little bit more disorder in the system. So now the magnetization will be a little bit smaller. Okay, so this is T not equal to 0. And of course, eventually you get to this point where the temperature is above Tc. So if we cross along this direction, now there shouldn't be any discontinuity at all. But the external field will, of course, still favor a magnetization that points a little bit along the external field. So what you're going to see in that case is that now there's no more jump, okay? So this is now a temperature that's bigger than Tc. So what happens then as a result is that as a function of this external magnetic field, if you sit below Tc, there will be a discontinuous jump in the magnetization. So we call that a first order phase transition. And if you're above Tc, there's no discontinuity at all. It's completely just a crossover from slightly negative to slightly positive, okay? So this regime, let's pick a color here. Actually, let's pick this color. So this regime is called a first order transition or discontinuous transition. And out here, we just have a crossover. Okay. And this point here is this kind of second order phase transition. So this Ising model, we think it ought to, and indeed this two-dimensional solution that Onsager found, has all these features that, that there is a first order transition as a function of the magnetic field below Tc. There is a continuous phase transition at Tc, and then above it, there's just a crossover. And so this Ising model is already an interesting model because those are features that real ferromagnets also have. And what is even more interesting, the Ising model is a toy model for a lot of other stuff that actually behaves similarly. So, so for example, look at the following. So look at so this superficially is a totally different system. So we look at a liquid gas phase transition in, say, ordinary water. So there's a phase diagram for that, which you can find on Wikipedia or in the textbook probably. And the way that there's different ways to draw it, but the way it's typically drawn is as a phase diagram in the pressure temperature plane. So this, you can think of this as, say, ordinary water, okay? So ordinary water comes in kind of, well, strictly speaking, comes in many phases, but roughly speaking, it just comes in 3. There's a solid phase, ice, there's a liquid phase, water, and there's a gas phase. And the phase diagram looks something like this. Okay, where you have so there's a solid here. So the solid corresponds to either very low temperature or very high pressure. There's a gas here that corresponds to low pressure or high temperature, and there's a liquid here. Okay. And so, for example, at atmospheric pressure, you can take the system and just heat. And so that's an experiment that in some sense you often do. So you could do this at atmospheric pressure, and you would just cross these lines. So this is heating at P equals constant, atmospheric pressure. And you see that if you do that, you encounter two first order phase transitions. One is where ice melts, and the other one is where the liquid boils. Okay. And these are discontinuous phase transitions because the density of the system changes discontinuously at that point. Indeed, when you boil, you can very clearly see this, that the system doesn't just continuously evaporate, it forms these bubbles. And the bubbles have a sharp transition between the gas, which is inside, and the fluid, which is outside. But you may also have heard that this first order phase transition between the liquid and the gas, it actually disappears if you increase the pressure. And so eventually there actually is a critical endpoint, is what this is usually called. So this, by the way, you've probably heard this is called the triple point. Okay, and this point here is called the critical endpoint. So what happens near the critical endpoint, so if you boil the liquid, again, you see bubbles, and the density inside the bubble is much lower than the density outside the bubble. And what happens if you increase the pressure is that that density difference becomes smaller and smaller. And eventually you have boiling where the density inside the bubble is now essentially the same as the density outside the bubble. And eventually you get to the point where that density difference disappears completely. And now you can no longer distinguish between the liquid and the gas. So there's no more discontinuous phase transition. You just continuously change the density of the system. Okay. So why am I talking about this? So the reason I'm talking about this is because the vicinity of this point is loosely analogous, actually more than loosely analogous, as we'll eventually see, to what happens in the Ising model. So roughly speaking, you can take the neighborhood of this critical endpoint and kind of blow it up. Okay. So then there are kind of two directions, one of which is sort of not exactly temperature, because again, this line of the liquid gas phase transition slopes a little bit. So, but there are two directions. One is not exactly temperature, but it's sort of temperature. And the other one is in principle sort of pressure, but in analogy with the Ising model, I would just call it H, okay? Although again, in the fluid, this H is really essentially pressure, okay? But this transition looks a lot now like the Ising model transition, because there's some kind of line. What jumps across that line is of course not the magnetization, it's the density of the fluid, but no, what's the, it's just some variable that jumps. And then eventually there is an endpoint, and beyond that endpoint, the density no longer jumps, okay? So here, this is really, there's a liquid side and a gas side to this, but the general features are very similar to what happens to the Ising model. And what is amusing is that we will discuss this later, that this is more than just an analogy. Okay, so the sense in which this is more than just an analogy is that the shape of the density curves in the vicinity of that critical endpoint is not just sort of, but it's exactly the same as the shape of the density curves of the magnetization near the Kerr temperature in a ferromagnet. And we'll have to explain a little bit later on why that is. But for now, I'm just bringing it up because it's one of the reasons why people are really, really interested in the Ising model, is that the Ising model is actually secretly more than just a model for a magnet. It's a model for all sorts of behavior that we see in statistical mechanics. Okay, so all of this was really just sort of a warm-up as to why it is that we're interested in the Ising model. Okay, and I already mentioned that in principle you could try to enumerate all states, but what I'm really trying to motivate here is to solve it by simulation. So whenever I write at the top of my notepad, I'm somehow accidentally hitting some button that I don't want to hit. Okay, so there's an algorithm for simulating the Ising model and for many, many models related to it, which is super, super simple, super easy to code. It's a very, very short computer program and just shockingly efficient. I mean, I actually do think it's the sort of most important advance in all of computational physics in the past century is the discovery of that algorithm. And it's almost not even a discovery because the algorithm is just so simple. So this algorithm is usually known as the Metropolis algorithm. So Metropolis was a person, there was a Nicholas Metropolis. And it's in some ways an example for a kind of larger class of algorithms, which is usually called Monte Carlo methods. So again, Metropolis was a person, he was working on early computers that was actually during the war at Los Alamos. And of course, the problem they were really solving was neutron diffusion in an atomic weapon. And they had very primitive computers, so they needed very, very simple algorithms that didn't take up a lot of computer space or computer time. And but they recognized just how powerful that algorithm was. So they actually took the time sort of on the weekend to write it up without the reference to the fact that really they were using it for developing atomic weapons. So there is a paper that's Metropolis, and somebody else. I think it's probably mentioned in the textbook what the paper is. And the algorithm, as you'll see in a second, it uses randomness in an essential way. So there's a place in the algorithm where effectively the computer has to throw dice. And so the name Monte Carlo simply refers to the Principality of Monte Carlo, where they have Monaco and its famous casino, so where people throw dice. So that's where the Monte Carlo comes from. Okay, so here's how the algorithm works. So it's just a very short algorithm. It has a couple of steps in it. So step one is just, you take this lattice and you pick a spin. It actually doesn't really matter how you do this. You can just pick a spin at random. Or what's really more commonly done is that you just sweep through the lattice. So you start at the upper left-hand corner and just one by one you go through the lattice, and once you're done, you do it again. So you can either do this randomly or you can sweep. Again, by sweeping, what you mean is simply you just go to every single spin in the lattice, and it doesn't have to be in a particular order. You can go through the rows, or you can go through the columns, or invent some more complicated thing. So that's the algorithm is very robust. You can do that in many possible ways. So you pick this spin. So the spin is currently pointing in some direction, either up or down. And what you do is you compute by how much do you change the energy of the system if you were to flip that spin. So you compute the change in energy for flipping that spin. And you should remember that that's a very cheap calculation, because every single spin computes to the total energy only through the interaction with its neighbors. So in a two-dimensional lattice, if you're looking at a spin I, it has only 4 neighbors, okay? So if you flip the spin in the middle, you only change these 4 terms in the Hamiltonian. That's the only thing you have to recompute. And even if you sit in 3 dimensions, the number of neighbors is only 6. So no matter what your lattice looks like, this is actually a very, very simple calculation, because you're only changing a very small number of terms in the Hamiltonian. So you compute the delta E for flipping the spin, okay? And so now comes what's usually called kind of an accept-reject step, which is we try to figure out whether we should actually flip the spin, given that we know how much that costs in energy. And the rule for doing it is very simple. So the rule is, if delta E is less than 0, then we flip. So if we lower the energy by flipping the spin, then we just do it, okay? So that would be one possibility. If you lower the energy, you flip, and if you don't lower the energy, you don't flip. But that doesn't simulate a thermal system. What that would do is you would eventually just drive it into the ground state. You would always lower the energy until you eventually find the ground state, but we already know what the ground state is at 0 temperature. It's just all spins aligned. So there must be some probability with which the spin flips up, so that it flips in such a way that you increase the energy. And roughly speaking, the way you should think about this is that, you know, the other spins provide a thermal reservoir, and we could always borrow a little bit of energy from that reservoir to flip a single spin. So there should be some likelihood for this to happen. And so if delta E is greater than 0, then we flip with a probability P that's e to the minus delta E over k Boltzmann T, okay? So remember that delta E is a positive number, so this probability is a number between 0 and 1. Okay. And so that's actually the whole algorithm. So you pick a spin, you compute the delta E for flipping, and then you have a rule that tells you whether you flip or you don't flip. And then you simply repeat over and over again. Okay. So the only thing you need is some kind of algorithm that allows you to flip a spin with the probability that some number between 0 and 1. And that's kind of where the Monte Carlo comes in. Let's make it a whiteboard. So, so how to flip with probability P. Well, it's very simple. You need a random number generator. So the easiest way to do this, and indeed all modern computers and, you know, Mathematica and Maple and Python and so on, they all have random number generators. And the simplest kind of random number generator is simply a thing that just returns a random number between 0 and 1. So that's the magic ingredient. So what you need in order to do this is you get a random number R, which is a number between 0 and 1, okay? So now we have two numbers between 0 and 1. We have this probability for flipping, P, which is a number between 0 and 1. And we now have a random number that's a number between 0 and 1. So all you do now is, if R is less or equal to P, then you flip. And if R is greater than P, then you don't flip. Okay. And this is simply an algorithm that ensures that in the long run, you really do flip with probability P, because if you have a random number between 0 and 1, I don't know, maybe it's helpful if I just draw a little picture. Okay. So you have a random number that's between 0 and 1. Okay. And now you got an actual number R, actual number R. Okay. So then what is the likelihood that this number R was, between 0 and P? Well, it's this area, which is just a fraction between P and 1. So by using this algorithm, you ensure that in the long run, you flip with the right probability, okay? And so this step, by the way, is sometimes called an accept-reject step. So roughly speaking, if we flip, then we had a proposed change to the spin, and we decided to accept. And if we don't flip, then we rejected it. And that's a common feature in many of these Monte Carlo type algorithms, that there is a sort of proposed change to the configuration and then followed by an accept-reject step. And the accept-reject step somehow ensures that the proposed change kind of occurs with the correct probability or the correct likelihood. Okay, so an algorithm like this, so number one, there's an element of randomness. So if you start from a certain initial condition and you run this Metropolis algorithm, since it involves calling a random number generator, if you do that, if you run your code twice, you're not actually going to get literally the same result. Although the way random number generators on most computers work, they're of course not actually truly random. So actual random number generators on computers usually have a seed. And if you use the same seed, you always get the same sequence of random numbers. So if you actually run your computer program, it's usually exactly the same. But if the number was truly random, then of course 2 incarnations of this Metropolis algorithm, step by step, are not the same. They will give you different configurations. The only thing we expect is that long-term averages are somehow the same. And so what you clearly need to do is you need to use this Metropolis algorithm, you need to run it for a long time so that it provides many, many instances of configurations of spins. And so effectively, after you sweep through all the spins, you kind of get some sort of new configuration. And then you sweep through all the spins again, you get another new configuration. And this kind of chain of configurations, again, that's usually called a Markov chain. So another word for these kinds of algorithms are sometimes Markov chain Monte Carlo algorithms. So again, this sort of thing that you produce here is called a Markov chain. And what we mean by Markov chain here is simply the following. So you have a lattice, and the spins on that lattice were somehow initialized in some way. So there's a configuration, let me call that S, which is you tell me what the values of all of these spins are. And then effectively, what a Monte Carlo algorithm like Metropolis will do is it'll take one configuration and it provides a rule to making another configuration. And then there's a rule for making yet another configuration. That rule has randomness built in. That's the Markov of this chain. So there's a rule that takes me from one member of that chain to the next one and has built-in randomness. So that's where the word Markov comes in. What's meant by a Markov chain is a kind of random chain. Okay. And so how do I now actually compute something like the magnetization? Well, what I do is I have this Markov chain of configurations, and in every one of these configurations, you can of course compute what the magnetization is. So in every one of these configurations, you can just compute, what is M1, and you can compute what is M2, and you can compute what is M3, and so on. And then the mean magnetization, so there's a mean magnetization that follows from the partition function, but the idea of this algorithm is that it can be simulated as the mean of the magnetization I see in this Markov chain. So the whole idea of Markov chain Monte Carlo is that the mean magnetization of my statistical mechanics model is just 1 over, oops, 1, I'm writing too deep down, oops. Okay, so the magic idea is that the mean magnetization is 1 over the number of configurations that you produced times a sum over all configurations of this M alpha. Okay. And the magic of Metropolis, of Markov chain Monte Carlo, is that this method works shockingly well. It's a super stable method, very, very reliable, very easy to code, and just useful all over the place. And so, and since this is so simple to code, you will eventually actually get a little homework exercise of trying to code this up. So if, by the way, you should let me know, by the way, if that's somehow currently posing a difficulty for you. So this can easily be done in Mathematica, it can easily be done in Python or something like this. So if you're currently in a place where you have trouble accessing either one of these things, you should let me know. In principle, if you happen to know Python, it's totally free, it can always be downloaded. And you have these beautiful Jupyter notebooks, so that's in principle a very useful tool. Might be, you know, if you're somehow bored, it might be a nice time to learn that anyway. Actually, the nice thing about these Jupyter notebooks is just like Mathematica notebooks, you know, if you have a homework assignment, you can in principle completely finish that within one of these notebooks and then just produce a PDF and, you know, save it for yourself and submit it as a homework assignment. So if you actually happen to have too much time on your hands, you know, that would be a nice thing to look at. But yeah, generally speaking, so this is all I wanted to cover today. Any questions? If not, I can stop here. I actually, I posted a Zoom link for tomorrow, which I kind of called a virtual office hour. In principle, if there's interest, I could actually make that one-on-one, or I could make it one-on-one in the future. But tomorrow we can just see if that's a reasonable time, if there are any questions. I could also maybe, since we never got around to talking about the midterm, I could talk about the midterm just a little bit and, you know, tell you what the plans for the future are. So if you have any questions, you can also just save them for tomorrow, and we can do that during the virtual office hours. So other than that, I hope that everybody stays healthy, everybody stays well, everybody's in good shape. If not, again, just please let me know.